Hello everyone. I hope I am audible. So this is the tutorial sheet, tutorial 9 of the measure and integration in NPTEL course measure and integration. And so let me start with this. And today is 20th September. Okay, so this is a tutorial 9. So in this tutorial, what we will discuss mostly the whenever you have a um, whenever you have a two measurable space whenever you have a two measurable space like x mu x is mu, there it is x is a set and s is the collection of all measurable sets, and mu is a measure on that. And suppose parallelly you have y, tau, and another measure lambda. Suppose you have to separate measure space, separate set, separate measurable space, and separate measure. Now, what is our target is to show that to define a new measurable sets, collection of new measurable sets on the product set x cross y, Cartesian product of x and y, and what is the corresponding measurable. First, we want to define the collection of measurable sets, and next we want to define the collection of all what is the measure suitable measure on that on that sets. And another is that also the one fact we have to do is that those two has to become compatible with the already existing thing like x s mu y tau lambda. Okay, these are the already existing thing. Okay, and so we have to be compatible, and what in what sense we are going to be say compatible, that we will be discussing on the way of this tutorial. And what else, and we will in particular we will see that if m1 is the Lebesgue measure on the real line, then m2 is the Lebesgue measure on r square. Now r square can be viewed as r cross r. Now with this I mean with this terminology, so one can give a new measure which is given by the which is coming from this as a product measure. So we will look at that product measure actually not equals to the m2. This is one other fact. So still they are compatible in some sense, and we'll discuss some problems which may help you to solve the assignments of this uh, weekend of this week. Okay, so let me start the um, throughout the tutorial. Today's tutorial we will consider x s mu y tau lambda are measure space. These are the today's standing assumptions. We will always consider these two facts. And what is mean that if you recall, X is a set and S is a special collection of subsets of X that has to be sigma algebra. Sigma algebra means this is closed under countable that should contains the empty set and the full set X, and it is closed under countable union, and it is closed under the completion. Okay, and similarly, and mu is a measure defined on the sigma algebra, that this sigma algebra is okay, this sigma algebra. So these are the things we are to consider as the standing assumptions. So first we will consider what is the uh, so our target is to give a measurable. Our target is to give a collection of or give a sigma algebra of subsets of x cross y, which is worthy to be the product of worthy to be the sigma algebra of the product space, to be the sigma algebra which is compatible, which is compatible with already existing sigma algebra S of subsets of x and tau, which is subsets of y, and provide a compatible measure which is compatible in the seminar, which provide a measure on that measure on that that sigma algebra on that sigma algebra which is compatible in the similar way. Okay, so this is our target. So what was the main thing how they have, how one consider. So here we will not discuss the compatibility, here we'll just discuss how it is defined. So for uh, any set, I mean, what we can consider, let's consider any subset, any subset E of x cross y, which is of the form ES times EY, where ES belongs to the sigma algebra S and EY belongs to the sigma algebra. Okay, better to not to give E tau. Okay, ES and E tau, which is belongs to the tau. This is the general form, and these are called measurable rectangle and finite disjoint union of measurable rectangle is called elementary set and the sigma algebra generated by all elementary set generated by all elementary set of x cross y is denoted by, is called the sigma algebra of, called the product sigma algebra called the product sigma algebra of s and y, s and tau, and denoted by s times tau. So this is what it is denoted. Okay. So why this is compatible? I mean, where in which sense this is compatible? So suppose you have taken a set E. E belongs to this S tau. So this is there is a already discussed lemma which is already discussed in class, such that for any x belongs to capital X, if we consider Ex is equals to all y such that all y belongs to capital Y such that x comma y is in E, then this is must be measurable set, and this set has to be is an element in the sigma algebra tau. Similarly, for any y belongs to capital Y, if one consider Ey is equals to all x belongs to capital X such that x and x comma y belongs to E, this one must be a sigma algebra. This one must be a measurable set in S. Okay. So now, so this is the compatibility we are talking about. That if we fix an element x belongs to capital X and we define Ex by this set, this has to be here, and this is the compatibility. So I mean, this set has been defined in such a this compatibility is there. Now, how the measure is defined? Now our target is to give a now target is to give a target is to provide a measure on this sigma algebra which is compatible in the similar way. That is how it is defined. Suppose you have a let E is a set element in there. Okay. Now what we have defined for every x belongs to capital X, we have defined Ex. Okay. Now this is measurable. Now if this is measurable, now define a map for every x belongs to. Let's take this is measurable and the element in tau. So therefore, tau of Ex is an well-defined function. Okay. And similarly, for any y belongs to capital Y goes to mu of Ey is also is a measurable set, is a measurable function, measurable function with respect to x, y tau. This is the corresponding to second one. Y tau. No, this is corresponding to the first one. X x s mu. Okay, and this is a measurable function y tau lambda. Okay, but here we need the sigma finite measure that we have to take in. Our target is to give a product. So in today's we will consider this and this are sigma finite measure space, because without sigma finite there must be some problem. But I will not discuss why there is a problem. So sigma finite measure space. Without the sigma finiteness, will be little problem. Okay, so um, so I will not discuss why there is a problem, but sigma finite measure space, if we consider, then these two will be the measurable function. So they are not only measurable, and so in that case, this is the measurable function. So if one consider d1x x d mu x, this is must be some value that can be infinite as well. And also similarly for this function, one should have this particular thing that y mu of ey and d lambda y. So this must be the interesting fact is that when you take the semi-finite measure space and if you start with do like this, then these two value has to be these two value will be equal. Okay, if you do start with the semi-finite measure space, I mean both of them are semi-finite measure space, and you define the sigma algebra like that way, then for every set, so then for every set E subset of S, E element in the S, this product which how we have defined, we have. Okay, I'll write little down. For every E belongs to, we have this one, and this is what it is defined as the measure. I mean this measure. This is what it is given as the measure of the set, and which is denoted by mu. This one. This is the measure on the measurable space x cross y with the sigma algebra S round. So this one can give this is as a measure. Okay. So now with this we will directly go to the some problem. So let's write the first problem. This is the basic definition which I should discuss, so that I have discussed. Problem 1. What it says, give an example of non-empty set X and monotone class. Okay, so before that, so let me write, and after that we will consider. Give an example of a non-empty set X and a monotone class of subsets of X which contains X and empty set, and which is not an sigma algebra. Which is not a sigma algebra. So what is monotone case? Monotone class. So one can question, what is a monotone class? So monotone class means, so basically what it is, basically what it is a collection of subsets of subsets, collection M of subsets of is called monotone class if it is closed under countable increasing union. and countable decreasing intersection. That is that is if AI corresponds to be a increasing sequence in M, increasing sequence in M, then their union must be scripted, and if bi equals to infinity, b and decreasing sequence be a decreasing sequence in M, that is bi superset of bi plus 1, okay, for all I belongs to script M. Then intersection of bi I equals to 1 to infinity belongs to script M. So this is what it is, countable union, and uh, it is closed under countable union, countable increasing union, and countable decreasing intersection. Okay, so this is what it is in monotone class. What it is asked: give an example of a non-empty set X and a monotone class M subset which is contains X an empty set but which is not a sigma algebra. So okay, let me try to give an example. Let us take let X is equals to close interval 0 to infinity. Okay, we can take infinity close as well. Then for any n belongs to natural number n, take a n is equals to 0 to n. Okay, and consider n is equals to, which should contains empty set union x, empty set x, and all an such that n is coming from real belongs to natural number. Then clearly this M is not a sigma algebra. M is not a sigma algebra, as 0 to 1 close interval is in here. Sorry, as yeah, as 0 to 1 close interval is in M, but its complement 1 to infinity is not in M. Okay, so but if a set is sigma algebra, then it must be closed under countable union and closed under the completion. But the completion is not there. So therefore, this is not a sigma algebra, not a sigma algebra. So let's check whether this is an monotone class or not. So now let's take. So is there any decreasing sequence? There is no other decreasing sequence one can get. Okay, like yeah, one can take if let ei, one can take decreasing sequence. For example, let's take um, let's take something like e1 is equals to am, e2 is equals to am minus 2, m minus 1. In that way, then clearly am is subset of am minus 1. I'm writing correctly, no, am is superset of am minus 1. So therefore this is, so that means E2 is superset of E1. So in this way, whenever you will reach to AM, that will be, I think, a 0. That will be only the singleton set 0, and other then a m plus 1, one can take just 0. One can take like this way, or one can take empty set, whatever it is. So this will be an decreasing sequence. So their intersection will be there. Okay. So increasing sequence, it is clear how one will get that an itself is an increasing sequence. And so my point is that so one can take decreasing sequence as well. So it is not I'm not saying that there is no decreasing sequence. Let I equals to 1 to infinity be an increasing sequence, then union of then if one ei for some I belongs to natural number, then their union I equals to 1 to infinity must be x. Otherwise, 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 union of I equals to 1 to infinity. Huh, this is what it will be, what is possibly be. Acha. So this EI, this will be is equals to now let us look at this. What is the EI? EI are the element in be an increasing sequence here. Important fact is that uh, here I must write that down because without that thing is not correct. This is an increasing sequence in M. Okay, so that means this EI will be either AI or MT or X. If none of them EI are X, so that means their union either it is MT or it is the maximum. I mean they can be AN. It will be like AM where AM is equals to um, maximum of AI such that AI belongs to this sequence. So that can be infinite as well. Okay, but whatever. If it is infinity, then it will be the full set. Okay, but that means that is there. Okay. So now similarly, one can show that script M is closed under countable uh, decreasing intersection. Okay, this is what it is. Now we will be looking another problem. Okay, so this will solve the problem. So now we'll be looking another problem. So let's write the problem. What it says, let p greater than equals to 1. Okay, let x s mu be a measure space. Measure space. Let f be a real valued function defined on such that integration x mod of fp d mu so that integration x mod of fp d mu is equals to p integration 0 to infinity t to the power p minus 1 mu at d mon t, where this et is equals to all those x belong to capital X such that mod of fx mod of fx greater than is equals to greater than p. This is what it is et. So what is the question? Question says x has me a measure space and f be a real valued function defined on x such that integration x mod ft d mu is finite. Okay, and show that this one holds. Okay, now let's try to find this one. Okay, it is clear that et is okay. F is what it is called. Let it be real valued function. So let's write f is a function from x to y. Given that f is a function from x to y, clear that the set such that mod of f is greater than t is measurable. Okay, this is very much clear. Measurable with respect to the usual level with the usual level measure. And no, this is okay. That is measurable, that's true, if the function is measurable. So the function is measurable obviously, but note that what it is says p integration 0 to infinity t to the power p minus 1 mu of et dm1 t. This can be written, this m1 is the and m1 is the Lebesgue measure, usual Lebesgue measure on real line. Okay, now this can be written as p integration 0 to infinity t to the power p minus 1 integration over x characteristics function on et and d mu this one with dm1t. Okay, now let's take f is equals to, here f is there, so let's take capital F. Capital F note that this particular thing, p minus p minus 1 characteristics function et at the point x as a function on or one can take, note that if is, this is the function, okay? This is real, this is positive, this is positive function on, this is not the full zero, this is not the full r, this is actually on 0 to infinity. I think this is, yeah, 0 to infinity. So on this is positive on this x times 0 to infinity, okay? Then by using, then by using Fubini's theorem, Fubini's theorem is the most, I mean, the most important theorem for this product measure. This Fubini's theorem, this interchange, this limit can be interchangeable. Okay, what is Fubini's theorem? That I will write in short here. Okay, Fubini's theorem: integration over 0 1 infinity t to the power p minus 1 integration over x characteristics function et d mu whole dm1 t. This can be written as integration over 0, I can change it, x times 0 infinity f of f with the product, here is the d mu times m1. One can give this one, okay? But this is also can be interchangeable. This is the Fubini's theorem. This is interchanging the um, interchanging the, so this can be written, note that et is actually 0 to mod fx. It is ranging value from 0 to mod fx. So this can be written as 0 to fx integration 0 to mod fx, because outside that, okay, basically main point is that I don't need full 0 to infinity basically outside. Okay, one can write this one. Okay, let me write this one, and after that one can 0 to infinity t to the power p minus 1 characteristics function et. This is at the point x, this is at the point x, dm1t. But note that this function outside of the 0 to mod fx is 0, okay? So therefore one can write this one as 0 to mod fx t to the power p minus 1 d, okay, this is interchange, this will interchange dm1t, okay, dm1t, and outside this is d mu x, okay? But now if we add p here, if we start with p here, then p, let's take p here, then it will be integration, and this function is on the finite interval, this function is remain integrable. So this is, one can do the usual remain integrable things, or you can use the absolutely continuous and the those things. And I mean that absolutely continuous things mean, if a function is absolutely continuous, or then its derivative is integrable, and the integration of the derivative is the difference of that 2 point where the integration is has been doing. So then it will be like t to the power p, and it will be like mod of fx to the power p d mu x, and this is equals to, this is what we have to prove, this is what we have to prove. But no, here we have thing, we have the fact that, okay, here we have not used the Fubini's theorem. I mean, we have used Fubini's theorem, but we have not used how, why the Fubini's theorem is applicable here. Okay, let me check that first. Why Fubini's theorem applicable here? And what is Fubini's theorem? In fact, we can. Fubini's theorem is very big actually. Okay, let me write the Fubini's theorem. Fubini's theorem. Let me write the Fubini's theorem. Okay, this is very important theorem. Let x s mu and y tau lambda are to sigma finite measure space. Okay, these are to sigma finite measure space. Okay, and if from x cross y to real continuous also will work, be a extended real valued function on x cross y, be an extended, I mean that can take value infinity as well, real valued function on x cross y and measurable with respect to like, or one can write in combine and s tau measurable. That means inverse image of every ray is actually inside an element. Then the following holds. First one is that if f is non-negative value, if f is non-negative value, if f is non-negative value, then for any x and y, then for any x belongs to capital X, y belongs to capital Y, the function phi x given by um, the function phi x given by fx y d lambda and f psi y is equals to integration over uh, x fy d mu, where are measurable function on x and y, function on x and y respectively. Here measurable means phi is measurable with respect to the measure space S, and psi is measurable with respect to the measure space Y. Okay, respectively, where these fx are actually the section. Fx is a function. Fx is a function from y to r, are given by fx at the point y is fx comma y, and fy is also section at the point y, that is also given by this one. Okay, these are the function, and one can and and here is the interesting part. One can interchange these two facts, and that will be d mu times lambda is equals to integration over x uh, phi x d mu, which is equals to integration over y psi y d lambda y. So whenever this is positive, main point is that whenever this is positive, so this is basically, if you look at here carefully, this will be x integration y f of phi at the point x, and phi at the point x is means fx at the point y with d lambda y. Okay, this one with d mu x. This is what it is mean. This particular thing is this one, and which is equals to integration. Acha, this is what it is. So this is means that x integration y f x y d lambda y whole into d mu x. And similarly, this particular thing is equals to what it is. This particular thing is equals to integration over y, integration over x, f x at the point y, okay, d lambda psi y is equals to integration x, psi y is actually fy, okay, psi y is actually fy, psi is actually fy at the point x, d mu x, and whole d lambda y, okay. So this is actually exactly equals to integration y, integration x, f of x and y, d mu x whole into d lambda y. Main point is that one can interchange the integration basically. So this is what it is, the Fubini's theorem. Whenever the function is non-negative valued, that in that situation we don't need anything except the fact that f is measurable with respect to this product measure. And second fact is that if the function given by phi star from x to r given by integration over integration over y, uh, integration over y integration over y, one can write it as mod of f. This is a mod function, and its slice at the point x, okay, its section at the point x, and d lambda. This is finite. This is exist finitely, is integrable, or the function psi star from y to r given by psi star y is equals to integration x mod of fy d mu, okay, is integrable. That means integrable means this is a new function with the variable y. Now we have to take the mod of that and integration, that integrability, that if a function is integrable if mod of f integration over x d mu is finite. That way integrability we are talking about. Here integrability means this is integrable. So that means that is the integrability and the integral are not same. Okay, if it is integrable, then the integral is defined in that way. Okay, so given by this one is integrable if and only if these combined two fact. I mean, any one of them can happen if and only if f is integrable with respect to the measure mu cross lambda. That is integration over f cross y, f mod of f d mu cross lambda is finite. And moreover, this is full stop, one can write. Moreover, in this case this interchangeable can be happened, that x cross x integration f x y dy y dx, this one is equals to integration x cross y f of xy d not dx. This is d lambda basically. D mu times lambda at the point x comma y. This can be written as y integration x. This interchangeable is possible. So this is the Fubini's theorem. So now using Fubini's theorem, why in our case in our case it is given that in our case we have to show that in our case the Fubini's theorem is applicable. In our case, mod of p0 to infinity I mean we can start from here. We can start from here. I mean we can do the reverse. In our case, as it is giving that mod of x, where is the x? Mod of x, integration x mod of fp d mu is finite, then one will get where we are using the Fubini's theorem, then we can use the Fubini's theorem at the appropriate position. What is the appropriate position here? So let's start from the reverse. Suppose f is a function and this holds. So then one can directly write, this one can be written like this, so there is no problem. Integration 0 to x and mod of fxp, one can write pt to the p minus 1, 0 to mod fx dm1. One can write, there is no problem. This step one can do. So, and now from here to here, there is no problem. This is just the same thing. Okay, writing differently. So now from here to here, we are using the Fubini's theorem. Here is the three step where we are using the Fubini's theorem. These three steps, in these three steps, we are using Fubini's theorem. Okay, so now using Fubini's theorem, if we do the reverse way, then you will get the answer. This is what it is, so this is done. So this completes the proof now. Completes solution of the problem. Okay, so this completes the solution of the problem. Now we will discuss another problem. Now let's focus on a new problem. So till now, whatever we have seen Fubini's theorem, we have seen how the product measure is defined and how those are compatible with the already existing measures things. Okay. So now we are trying to solve a new problem, and whatever theorem we will be recording, while we record, we will be recording those theorems. So yeah, for x greater than 0, so that integration 0 to infinity e to the power minus xt dm1t is equals to 1 by x. Okay, now note that. Recall that whenever monotone convergence theorem was there, that monotone convergence theorem is says that if a sequence of function is non-negative and that converges pointwise to a new function, then uh, I mean one can consider this is the if a sequence of fn is a sequence of monotone convergence theorem. I'm shortly writing. This is not the exact statement. I'm not writing exact statements. Fn is a sequence of non-negative measurable function with a standing measurable set x and y, and fn's are actually real valued function on that measurable space. I mean there is the x s mu is a measurable space and f is a function from x to r. This is what it is, a non-negative valued. Okay, and such that fn converges to a function f, and then fact is that f will be measurable and non-negative value. There is no doubt about this. And if fn's are also considering that fn's are non-negative integrable function, if I consider not only measurable, when you are considering integrable, that means this function is already measurable. Okay, integrable functions, then integration over x fn, this limit n tends to infinity d mu, this must be as integration over x d mu. So now with this, as the function e to the power minus xt, so now here come back to the problem. As the function has e to the power minus xt greater than 0 for all x greater than 0, in fact x, even x is less than 0 still doesn't get a problem. On So for any x greater than 0, for all x greater than 0 and t belongs to closed interval 0 to infinity. So then what we can say, the characteristics function for h n belongs to natural number, the characteristics function 0 to n with product e to the power xt can be considered as fn xt. Okay, fn t, sorry, fn at t. X is fixed right now. Okay, this is fn t. This is a function of t one can consider, and that converges to the function e to the power minus xt for some fixed x. Okay, for all t belongs to, so one can write for all t belongs to close interval 0 to infinity, and for a fixed x greater than 0. So therefore we can use the monotone convergence theorem. Then using monotone convergence theorem, we get what we get using monotone convergence theorem. What we get, integration um, 0 to infinity e to the power minus xt dm1t, that can be written as limit n tends to infinity integration 0 to n dm1t. But this integrand is remain integrable. Remain integrable. So that gives, then this gives limit n tends to infinity 0 to n e to the power minus xt dm1t, right? So now this can be written as limit n tends to infinity e to the power minus xt by minus x 0 to n. This can be okay. So now this can be written as dt only. So now this is minus x. Okay. So now if we replace t equals to n, what we'll get? Limit n tends to infinity. If we replace t equals to 0, then it will reverse. Minus is there. So first term is this one basically e to the power minus xn by x only. Now for fixed x, we are doing everything for the fixed x. Now if I take n tends to infinity, that for fixed x greater than 0, here is the fact we are using x greater than 0. If x is greater than 0, then this term will go to infinity. So e to the power minus infinity will go to the 0. Okay. Okay. Now, so this can be written as 1 by x. Note that for a fixed x greater than 0, e to the power minus x and t converges to 0 as n tends to infinity. So this is what it is. This is the first part. Okay. This is what it is you have to prove. So this solves the problem. Now let's do another problem. I mean this problem, part of this problem as n tends to. So this is done. Okay. For fixed x greater than 0, here is x greater than 0 is using heavily. And now for the another part. So for another part, what is says part B. Part B says use the above relation and Fubini's theorem to show that limit n tends to plus infinity basically 0 to r sin x by dx is equals to pi by 2. So here we have to use the Fubini's theorem. Okay. So now what we get here is that first of all recall from the recall uh, from the last from the first part of this problem. What it says 1 by x is equals to integration over 0 to plus infinity e to the power minus xt d m1t. Okay. So now if we replace this one, then what we'll get? Then limit r tends to infinity. Sorry. Okay. Limit r tends to infinity 0 to r. This is not real, this is some positive r. 0 to r sin x by dx, which is equals to, is can be written 0 to r sin x into 0 to infinity plus infinity e to the power minus xt d m1t and d. This is also Lebesgue measure, but right now we can write dx. But next part one can write this one as 0 to r, 0 to 0 to not 0 to r, 0 to r this way, and 0 to plus infinity this way, and sine x e to the power minus xt dm1t and dm1x. This is what it is. Now this is the product measure we are using here. So now this is what we are getting. Okay. Now note that the function f from 0r cross 0 to plus infinity to real number given by f of x and t is equals to sine x e to the power minus xt is integrable with respect to the product measure is integrable with respect to the product measure m1 cross m1. Indeed, why that is integration over this particular thing 0 r times 0 to plus infinity. Okay, this one into mod of fxt d m1 times m1 at the point x comma t. This can be written as less than is equals to 0 to r 0 to infinity and mod of fxt is equals to sin x. Mod sin x is less than 1 e to the power minus xt, that is positive, so therefore it will only remain e to the power minus. Okay, whatever it is, this one is the mod fxt. So mod fxt one can write this one is less than is equals to integration 0 to r sin x by x dm1x, but this is finite. Why? The limit, as limit x tends to 0, sin x by x is finite, and other side it is also finite, so therefore this is finite, so this will exist, there is no problem. Okay, this is remain integrable, that's why, I mean, if I take some t greater than 0 and if I consider t to r, then that is remain integrable, so that's why that is Lebesgue integrable and that has to be equal, so that's why it is finite. And if we take only the t equals to 0 point, then at that point limit exists finitely, so therefore that will exist. Okay, so this is finite, so therefore then we can use Fubini's theorem. Then integration 0 to r sin x by x dx, which can be written using the change of integration 0 to plus infinity. I think there will be a little problem. Just a minute. Now this one we can use the partial integration in you can use the partial integration. So let's take this one is the y. So I want to obtain this one. I is equals to this, and this one is equals to 0 to r sine e to the power minus xt dx. And if you use the partial integration, it will be cos x. I mean, first we will be keeping e to the power minus xt fixed, and now integrating sin x, that is minus cos x, and differentiating the first term, that will be minus minus plus cos x e to the power minus xt by x. Okay, this is the first term, 0 to r. This is the, I think t is here. Okay, integrating that one and differentiating that one. So differentiating that one, that will be t is here, t dx. Okay, now again doing the, okay, let me replace this value. If you replace the value cos r e to the power minus tr, and if you replace the value of x equals to 0, then cos 0 is 1, and that will be 1 again, and that will be minus minus plus. Okay, so minus t into, if we do the again partial integration, what it will be, cos x, integration of cos x will be sin x and e to the power minus xt. Again you can replace value 0 to r, and the second one will be derivative, sorry, integration of the cos x, that is sin x, and again integration of e to the power minus xt, that will be plus e to the power minus xt, and one t will come outside, 0 to r dx. Okay, this is what it is. Now what you will get if you do it here, so this one is the, if you look at, this is again the term I1. Okay, so there it will get 1 minus cos r e to the power minus tr minus t into, if you replace the value of r, then first it will be cos r into e to the power minus tr, and if you replace the value 0 here, so sin 0 is 0, so that's why it is done, it will done, and this is the, and this will be the minus t square into the value I. Okay, the integration, the starting integrand point. Okay, starting integration point. So therefore one will get that I is equals to 1 by 1 plus t square, 1 minus e to the power minus tr cos r minus t e to the power minus tr cos r. Okay, sorry, I think this will be sin r. Okay, sin r. Okay, now if I take, now limit r tends to infinity, integration 0 to r sin x, or one can write 0 to r sin x so this is what it is, I1. Okay, now one can write 0 to infinity first place, second place 0 to r sin x to the power minus xt whole dm1 x, and this is dm1t. This can be written as limit r tends to infinity 0 to plus infinity. This is not the closed interval, this is the open interval, and this one is got the value 1 by 1 plus t square, 1 minus e to the power minus r tr cos r minus t to the power sin r first e to the power minus tr. So this is what it is, and dm1t. Okay, now what it is, what you can do here is that, now note that mod of 1 by 1 plus t square 1 minus e to the power minus tr cos r minus t sin r e to the power minus tr. This particular value, this is less than is equals to, first of all, this one will be less than is equals to cos r is less than equals to 1, sin r is less than equals to 1, so therefore it will be okay, so therefore it will be 1 plus t square and e to the power r minus 2, that is also greater than g greater than 1. If r is greater than 0, note that if r is greater than 0 and t is greater than 0, then e to the power minus tr has to be greater than 0, whatever tr it is. So that means e to the power minus tr has to be less than 1. Am I correct? At the point 0, it is giving value 1. So below 0, it will give value less than 1. So this is correct. So therefore, mod of this term will give 1 by t r square, mod of this term will give 1 by t r square. So this will give 2t r square plus t e to the power minus tr mod by 1 plus t square. This is what it is. So now this will go to 0 as r tends to infinity. Okay, this particular term will go to 0, not the full one. Okay, this term will go to 0 as r goes to infinity. Therefore, then this then 2 by 1 plus 2 square plus t e to the power minus tr mod by 1 plus t square goes to 2 by 1 plus t square as r tends to infinity. Then one can use dominating convergence theorem. That says dominating convergence theorem that says um, okay, and we get how the dominating convergence theorem one can use. You can take a sequence Rn which converges to infinity, and you'll correspondingly consider this particular thing as the FRN. Okay, now one can use the dominating convergence theorem, and then we can take that limit n tends to infinity inside, and because this is dominated by this function and that sequence will be dominated by this function. Okay, one can take those functions as the dominated as the sequence of functions whenever Rn goes to infinity. For each Rn, let's take a sequence Rn, and each Rn goes to infinity. For each Rn, whatever it will be, this will be called a function frn, and that will be dominated by the function t by 1 by t by 2 by 1 plus t square. And next you can use the dominated convergence theorem, and we'll get whatever we'll get, that then this particular integral will be equal to, then this will be equal to, this will be equals to, this will be equals to limit 0 to r, sorry, 0 to infinity, because that does not depend on limit r tends to infinity. Okay, we can write it inside 1 minus e to the power cos r minus t sin r e to the power minus tr 1 plus 1 by t square d m1 t. Now if we take limit r tends to infinity, so note that these two term will go into 0, these two term will go into 0. So this will only leave integration 0 to infinity 1 by 1 plus t square dm1 t. So again one can use the dominated convergence theorem, or one can write this on this form, but this integral is remain integrable on this particular interval 0 to n for any positive integer n. Okay, for any positive integer n, in fact without integer also, but one can do for integer, and that is remain integrable, and that is equals to limit n tends to infinity 0 to n 1 by 1 square dt, which is equals to limit n tends to infinity tan inverse n 0 to n, which can be written as pi by 2. So this is what it is. So this is what it is. We have to prove. Okay, this completes the solution. Actually, this completes the solution of the problem. Okay. So here is one point you can look at. Here we have used dominated convergence theorem. Sorry, here you can use DCT or MCT. How we have used the dominated convergence theorem or modern convergence theorem? Here you can give a short argument here. For each n belongs to natural number, consider the function 1 plus t square into characteristics function on 0 to n. Okay, this is as fn. It is clear that these fn are positive. Obviously, they are positive function on 0 to interval, and they are greater than equals to 0. And this fn converges to 1 by 1 plus t square is equals to f. So integration over f dm1, that is equals to limit n tends to infinity integration over fn dm1. So whatever it is given here, that we can take integration over f dm1. Okay, and now whatever is whatever is uh, now this is the dm1. Okay, one can, this is the dominated convergence theorem we are using basically. Okay, so one can write it here as 0 to infinity, and here is also 0 to infinity, but here is also, here is, it is supposed to be 1 plus t square into characteristics function on 0 to n. Okay, this is supposed to be, but and over 0 to infinity, but you know the characteristics function, so we can directly convert it to the 0 to n interval. Okay, this is what we are doing here. So we'll go to the next problem, but for that, before that, we'll take little. Okay, so we'll now try to do another problem. So let's, okay. So now let's try to do another problem. let f, g and h, three function, be integrable real valued function defined on r to the power n is a fixed natural number, so that so that f star g, what is f star that I am going to say, and h are well defined and they are equal. Okay, so where f star g is a function from where it is defined on r to the power n, okay, to the real valued function given by f star g at the point h, sorry, f star g at the point x is equals to integration over f x minus y gy d with respect to the product measure dmn times, so this is single measure, dmn y. This is what it is. The um, yes, this is what it is. If this is over Rn. So f star g, actually this is called convolution. F star g. Um, so convolution is first proving the first one is that with the if we consider convolution as a product on the set of all integrable functions, okay, then that product is commutative. This is what it gives. Okay, okay. So that means, so if we consider the convolution as the product, I mean product, one can give product as the pointwise product, or the like here it is convolution, and another is the composition. But composition, in that case we have to take n, the natural number n here, that has to be taken 1. Okay, okay, or otherwise function has to be taken Rn valued function instead of real valued function. Composition is only possible whenever both the domain and codomain are same, basically. At least domain and codomain of one sided, like codomain of f, sorry, domain of codomain of g and domain of f has to be same, but that is little problematic. Domain and codomain both have to be same for f and g in that situation. But without that, in general, one can define the product, that is by pointwise, and one is the convolution. This is called convolution. And this is the Lebesgue measure. DLMN, this is Lebesgue measure. This is called convolution. This is actually says commutativity of the convolution. And this is associativity. Okay. So let's start with the, let's start to prove this one. Okay. So first part, what it says, f star g at the point x is equals to integration over Rn f of x minus y gy de m1 m not m, m1 again m1 y. This is what it is. Okay. Now this can be written as, now with the change of variable, let's take x minus y is equals to u. In that y is equals to x minus u. So then g will convert to x minus u and f will be fu dmn and y will be, and this is the variable change basically. So then y will be, x is fixed right now. Okay, as x is fixed, so dm y will be dmu, but I think minus somewhere, there must be some minus. No, this is correct. So now this can be given and over r to the power n, and this is what it is, r to the power n g x minus u fu d mn u. This is equals to g star f at the point x. Okay, so this is what it is. And now second is that, so this gives the first. Now for the second, that one can give the, I mean, suppose you have three element FGH. Now how one can give the product? There is two way one can give the product. I mean, suppose you have the space of all integrable functions with respect to the Lebesgue measure del element. Okay. Now if you have three integrable function, you are giving the product by this way. Now if you have three element FGH, how you can give the product? Now there is two way one can give. First, make the product of f star g and then h, or make the product of g star h and then make h, make product h, that way. Okay, but these two has to be equal, then we can say the well definedness. So to proving well definedness, we have to prove that these two are actually equal. This is what we have to prove. Okay, so let's start with f star g star h. First this and then this. So this is at the point x is equals to integration over r to the power n f star g at the point x minus y and hy dmn y. Okay. So okay, I think dmn usually denoted at the below, not the above. Okay, what it is denoted? Okay, this is denoted by here. This is what it is. So now one can write here integration r to the power n, integration r to the power n. One can write here x minus y minus xi and g xi dmn xi over whole over integration dmn y. Now as the function, now note that, now consider capital F is a function from Rn times Rn times Rn to R given by f at x, y, z is equals to f x minus y and gz, then integration over Rn cross Rn f x y mod dm1 dmn xi dmn y for fixed x, okay, belongs to Rn, what it will be? This is less than is equals to integration over Rn times Rn mod of f x minus yj mod of gj d, here it will be product basically, dmn at the point yj. This is what it is, okay. And now what we have to prove is that this is finite. Why this is finite? Because just a minute, why that is finite I am going to. Now this can be written, first of all, okay, dmn times mn at the point yj, okay. Now first of all note that this can be written as Rn, note that, or here note that f is, or g is integrable, one can take g is integrable, then this is by, I mean, just directly following from the fact that f and g are integrable. So as g is integrable, what one can say? Think this as a function of y and z, and now for fixed y, if we consider it as a function of xi, then what it will be? It will be like f x minus y minus xi mod of gj, okay. Now right now we have fixed x and y both, okay. So therefore let's fix xi and x, integrable. Then for any xi belongs to Rn, the function xi goes to g xi. This is a constant right now, and the mod of fx minus xi is integrable. Why that is integrable? Why that is integrable? Because integration over mod of gj mod of fx minus xi dmn at the point y, this is what it is over Rn. Indeed, one can write. Indeed, this one, obviously mod of gz is there. There is no problem. With translation invariance, one can convert it for fixed x and y. Rn mod of gz mod of fxy. as Lebesgue measure is translation invariant. Measure is translation invariant. As Lebesgue measure is translation invariant. And now f is integrable and g is constant, so that will be less than finite. So this is what it is the reason. So now for this for this for this we can use Fubini's theorem. Then using Fubini's theorem, one can get that we can we can separate. That's the main point. We can separate that is integration over Rn mod of G integration over Rn mod of x minus y dm n y whole into dm n Okay, this is what it is. Okay, now, and that is finite. Okay, this is the reason actually Fubini's theorem. So this is so therefore whatever we have got that look at that this thing actually the same with the previous thing. So this is the same thing. So now one can use the this is finite. This is finite. Okay. So or one can this is finite. This one then one can use okay let me clearly make it. Now one can use the Fubini's theorem and now one can use the Fubini's theorem to star, and consequently we got mod of f star g star h at the point x is actually is equals to one can interchange the integration is equals to integration r n g of xi, right, g of xi integration rn f x minus f x minus y minus xi f x minus y minus xi dmnn dmn, this will be y, and okay, I think there must be, I have missed something. Yes, there must be some hy. This one. Okay. Now using the translation invariance thing, what we'll get? I want to get that G will be, what we want to get that F star, we have started with F star G star H. I want to get F star G star H. So for this region, what we want, if it is at the point X, first it has to be F at the point X minus Y, G star H at the point Y. That means G star H means G has to be Y minus J H J D J. This is what we have to get. Okay. Now change variable. Let's take X minus Y minus J is equals to U. In that case, what it will be? X is fixed. In that case, J will be X minus Y minus U. And Y will be X minus J minus U. Okay. In that case, let X minus Y minus J is equals to U. In that case, dy. So in that case, it will change to Rm. Here is the variable is x is fixed, y is fixed, only y. So here y and j. So if we take this is then equals to u, so y will be getting like this way. So this will be like f at the point u, h at the point x minus j u, d m y, d m n j. Again using the Fubini's theorem, what we'll get? We can do change the integration. So now what will be now? It will be f u will be outside, integration r n g j y, g can be written like f g h, right? So f is here, h x minus j minus u, g j d n y. Here using Fubini's theorem. Here we are using Fubini's theorem. So now what we'll get? This one is equals to integration r n f y. So now if we look at carefully, it will be h. It will be, we can, okay. Now it will be h star g at the point. What it is at the point? It is at the point j. So x minus u, right? This one whole into d m and y. But here I can again use the previous theorem by part A, h star g at the point x minus u can be written as g star h at the point x minus u. So can be written as fu g star h at the point x minus u d mnu, and now this can be given as f. This can be given as g star h star f at the point x, right? Okay, sorry, here it will be, why this y came? Okay, this will be u now.
This will be no. This is yeah. This will be u now. No? This hx. Sorry. Where is the changes? Hu. This will be u. This will be u. So now this will be x, okay? But now again using the fact that f star g star h at the point x. So therefore what we got here actually, therefore what we got f star g star h is equals to, here is also the we are using the fact the same logic we are using here. So this one is equals to f star g star h, okay, this is what it is, okay. So now this gives the well definedness. What is the question initially? Question was um, question was so that f star g star are well defined and they are equal, yeah. So this completes the solution of the proof. This completes the solution of the problem. So now we have very short time. I will try to do a very easy problem. So let's look at if I am able to find. Okay. Now the next problem. I think last one is problem 5, right? 4. Problem 5 now. Problem 5, what it says, we have seen the convolution. Let f and g be integrable real valued function defined on Rn, n is a fixed natural number, so that f star g cap is equals to f cap dot g cap, where this cap are actually the Fourier coefficient. F cap is equals to for example just where okay, here the Fourier series is are. So here for where f at the point xi, where for any xi, for any point xi belongs to Rn, f hat at the point xi is equals to integration over Rn e to the power minus 2 pi I x dot xi. What is this dot? This dot is some specific, that is fx dn and x, where x dot xi is equals to summation by xi I, summation xi I, this is real value, so this is what it is, I equals to 1 to n, this is what it is. So f hat xi is equals to, this is the Fourier series expansion, I think this is the Fourier series, f hat xi Fourier transform basically. This is not Fourier series. Whenever the underlying set will be the natural number, then it will be underlying set r to the power n will be natural number, then it will be the Fourier series. Now it is Fourier transform. This is the Fourier transform. We can write here. So here is interesting fact is that if you take convolution and take the Fourier transform, then whatever the Fourier transform already, if you take separately Fourier transform and then take them, this is the pointwise product. You'll get the pointwise product. This is pointwise, not pointwise product because um, no, this is pointwise product. Okay. So now, so f hat xi is equals to r n e to the power minus 2 pi I x xi fx dmnx. So this is what it is. Okay. So let me check now with this. Let us solve this problem. So f star g hat at the point x by definition is equals to r n e to the power minus 2 pi I x dot xi x star z at the point x dm and x, and which can be written in the form that integration r to the power n. Now we will be using the convolution. What is the convolution? That f at x minus y g of y dm n y. Now again using the Fubini's theorem. Here we are not using the how the Fubini's theorem are using. So this can be written as, here we can use the using Fubini's theorem. Check how the Fubini's theorem is applying. That means check that Fubini's theorem is actually applying. That means one can write it as, I'm not writing how the Fubini's theorem is applying. So integration over Rn f of x minus y e to the power minus 2 pi I x dot xi. Okay, dmn x whole into dmn y. Okay, now here we will be using the translation of invariance. Here we will using translation invariance of the Lebesgue measure f of u. Let's take x minus x minus y is equals to u. Then what will happen? That x is equals to u plus y. So then it will be e to the power minus 2 pi I x dot xi will be now u dot xi plus, this is component wise addition, y dot xi. Okay, d n x will convert it to u whole into d n and y. So now this can be written as r to the power n gy integration r n, sorry, this is r to the power n, not below. Yes, r to the power n. So this will be now fy e to the power minus 2 pi I u dot xi dmn u whole into e to the power minus 2 pi I y dot xi dmn y. Okay, so now what we'll get here, we have started with the fx at the point x, but where is the x now? X is, no, I think we have to change little differently. uh, fx minus y dmn x. So x is not obviously, yeah, so here is the problem I made. This is xi, this will be xi. So this will be Jai. So this will be Jai. Instead of changing all of them, let's convert the previous one. Jai. For some Jai, this one will be like GY all the way. This will be like DMY. So this will be F hat. This particular thing will be, this will be F hat at the point Jai into to the power minus 2 pi I y dot Jai dmny. So this will be equals to F hat Jai dot G hat Jai. Okay. So this completes the solution of the problem. Okay. So this is all for today. I'll stop here, and for next tutorial will be next Saturday from 6 to 8 p.m. Thank you.